All right. Last portion of the FERP. Let us all rejoice. We have made it here. So acid base. This is the most recent. So this is probably the most fresh in everybody's mind. Complete the chart below by placing an X in the appropriate column. I don't know what I was going for there because that doesn't make much sense, does it? So instead, what we're going to do is just fill this out as it pertains to these things. So 1 to 6, they're neutral 7. 8 to 14, of course, is basic there. And now let's go through and just fill out each column itself as it applies. These do taste sour, like our lemon and our Warhead sour candy and anything with that citric acid, that acetic acid, all that fun stuff. This would be watery because it doesn't have the... because it's an acid, and you'll see what happens when we touch bases as opposed to that instead. It sure does react with metals. That produces the H2 gas, which is what the bubbles are that you saw in your labs. Identify the ions produced. Of course, it is the H+, the hydrogen ion. pH paper, red, orange, yellow, right? So kind of like the first portion of our electromagnetic spectrum and our visible spectrum there. Universal indicator, it does turn it red, orange, yellow. Totally could have just duplicated that, right? And it is clear in phenolphthalein. That's the fun word to say. There is no taste. No taste in water because that's neutral. It is watery because it's water. It does not react with metals. There are no ions produced, so we'll leave that one blank. And it turns pH paper green. It turns universal indicator green, and it is clear in phenolphthalein. And last but not least, there is a bitter taste to our bases. It is slippery. It might be if you touch the basic solution that you use to prep your t-shirts for your tie-dye, then you might have felt your hands were a little bit slippery there too. It does not react with metals, and it produces the hydroxide or OH minus ion. And again, minus and plus, these are just +1, -1. Again, chemistry, if it's a 1, chances are we don't want to write it for some reason, right? And then, of course, it's going to turn our indicators blue, purple. Think base blue, right? That's what I always say. That helps me out. And, of course, it turns phenolphthalein pink, just like in our titration lab where we're trying to get that real faint pink color. Arrhenius. Arrhenius just means that it separates into its ions. So CaOH2 is aqueous, and that's because it dissolves and into separates in its ions. It dissociates, we say. So calcium is a +2 charge, and because it's dissolved, it is aqueous. Plus, hydroxide is a -1, and there's 2 of them, so I need to make sure I include that 2 out in front. Right, now we show is Arrhenius acid. The only thing that makes this acid and the other one base is the ion that you see, hydrogen or hydroxide. So we have HNO3 or nitric acid, and that dissociates into hydrogen ion and a nitrate ion, -1. Right, so again, it's those ions. Not exactly a decomposition reaction. You could kind of see a similarity because it starts with one thing, ends with multiple, but these are the ions that it dissociates into. Conjugate base. Conjugate base. What makes something a conjugate base or a conjugate acid? Well, it depends on if it gained or lost a hydrogen ion. Bronsted-Lowry tells us that acids donate, and let me do this. Acids donate or give, right? the hydrogen ion, and then bases take the hydrogen ion. That's why acids turn into conjugate bases, because they get less acidic since they're losing a hydrogen. Bases form conjugate acids. They're becoming more acidic, so because they're getting that hydrogen from them. So the conjugate base, well, that's when this hydrogen goes bye-bye, right? And that means that all that's left over is bromine with a -1 charge. Because remember, the hydrogen's also called a proton because it has a +1 charge. It's one proton in the nucleus. One hydrogen goes away at a time, so we're left with one other one here. We get more negative by 1, right? And then do the conjugate acids. So this is when they are gaining. So these both donated H+. Now these are going to accept an H+ since they're bases compared to acids, which means this is HOH or water. You could write it either way. I like writing HOH because you could see the acid and the base side of it because it is amphoteric, which means it has the properties of both an acid and a base because it has both of the ions that make something an acid or a base. Fun stuff there. NH3 is going to accept another hydrogen, making it 4, and because it accepts another one and it was already neutral, now it gets more positive by 1. Pay attention to your ion charges. Pay attention to them. Record the resulting conjugate acid and conjugate base from the following Bronsted-Lowry reactions. So you will know what's the acid, what's the base, so you know what's giving and what's taking a hydrogen. We have this hydrogen going to that base there. The conjugate acid is formed by what's getting or receiving the hydrogen, which is the base here, which is water. It turns into a hydronium ion, +1, right? H3O. How do I know it's a +1 charge? Well, H2O doesn't have a charge here. It's neutral. It's content, and then it gets more positive by 1. And conversely, the NO3 gets more negative by 1, and it happens to have a -1 charge anyway. If we were going to put states of matter to these, remember everything is aqueous except for water, which is liquid there. All right. A solution has a pH of 8. Calculate the following values. Well, if I wanted to calculate this, I would take the 10 to the negative pH value. This is 10 to the negative pOH value. pOH is usually negative log of the OH concentration, but because I already know pH, all I have to do is say that pOH is 14 minus that. So pOH is 6. 10 to the negative 8 is going to give us 1 times 10 to the negative 8 molar. And conversely, 10 to the negative 6 for the pOH is going to give us 1 times 10 to the negative 6. Yes, you need that 1 there. Please show all calculations with units. Titrations. Remember our equation here. The number of hydrogen ions in our acid times the molarity of the acid times the volume of the acid is equal to the number of hydroxide ions in our base times the molarity of our base times the volume of our base. Very similar to our dilutions equation. So we go through, and I'm just going to make a nice little given and unknown inventory here, just so I have it. VB, and then I'm going to duplicate this over, whoops, think smarter, not harder, right? That's the whole thing. Smarter, not harder. All right. So in this case, over here, we have that many milliliters of lithium hydroxide, so volume of, and the hydroxide, lithium hydroxide is our base, so that is 12.64. Now, again, in my previous video, you saw me change it to liters. I like operating in liters because That's what I think of when I think of molarity and using concentrations like this. However, because volume appears on both sides again in this equation, it does not matter. It's a ratio between those volumes. So you can leave it as milliliters, and it might be a little bit more practical for you to see it as milliliters because our liters values are going to be very small in comparison. It's kind of going to be a pain to work with. So let's leave them as is. I know the volume of the acid is 17.99 milliliters. I see that there is 1.5 molar hydrobromic acid. There's one hydrogen in hydrobromic acid, and there's one hydroxide in lithium hydroxide. And it's asking me for MB. So I'm using the equation above up here to work through this. So I get 1 times 1.5 times 17.99 equals 1 times molarity of the base times 12.64. And then we solve. Let me do that in the calculator so that you have it. All right, 1.5. Obviously, I'm going to skip the ones because I'm a chemist and we don't like ones. 26.985 equals 12.64 times molarity of the base. Drop the base. And once we do that, the molarity of the base is going to be 2.13 molar lithium hydroxide solution there. All right, and we'll do something very similar here. Last one of the whole FERP. That is awesome. Hydrochloric acid, that is my molarity of the acid. There you go. Only one hydrogen there. 2 hydroxides in the magnesium hydroxide there. I'm looking for how much of that acid I need to neutralize this much of base with a concentration of that. And we plug it on in. My equation is above 1 times 0.35 times volume A, which we don't know the volume of the acid. That's what we're looking for. It's 2 times 0.4 times 82.5. Doing a little bit of math here. Simplify both sides. Make things so much easier for yourself. 0.4 times 82.5. And that gives us 66. Divide both sides by 0.35. And you end up with your answer in milliliters. And it does ask you for milliliters, right? Pay attention to that. Just a little attention to detailing there, and you should end up with 188.57 milliliters. All right, so I hope that this all helped you out, regardless if you watched all of the videos, none of the videos, and if you didn't watch any of the videos, then you might not be even hearing this right now, but it's okay. But I hope that this series of videos and parts just helped out just a little bit for our final. So that's all I've got. If you have any questions, send me an email. Adios.